Hey, good morning, everybody. Welcome. It's my great pleasure to introduce Julia Cisneros this morning, Dr. Julia Cisneros. Fun fact, Julia is an Austin native. You don't meet those very often, so it's kind of fun to know that about her. She credits her entry into the geosciences during high school time here in Austin. She attended a 3-day program at A&M that was targeted to underrepresented students, and she was first introduced there to alien dune stratigraphy, and her life was forever changed. She went back to A&M to get her BS there and completed an undergraduate thesis entitled Morphologic and Computational Fluid Dynamic Analysis of Sand Dune Topographic Obstacle Interactions on Earth and Titan. So she jumped right in there, and then went on to receive her PhD from the University of Illinois in Urbana-Champaign in 2021, where, working with Jim Best, she developed a method for quantifying bedform morphology and movement tracking. Her work on large rivers, including the Amazon, Mekong, Mississippi, Missouri, Parna, and the smaller river wall, was published in Nature Geoscience in 2020. As a Tejana, Julia is dedicated to increasing diversity, equity, and inclusion in the geosciences. During her graduate career, she created, developed, and led a geoscience camp for girls targeted to middle school girls in the Urbana-Champaign area, and served on the GeoLatinas Leadership Council. She continues this work as an early career researcher focused on institutional efforts to improve DEI, for example, as a co-author on the 2021 Nature Communications paper, An Actionable Anti-Racism Plan for Geosciences Organizations. And stay tuned for a forthcoming publication accepted to the Journal of Geoscience Education. Julia's current research focuses on the key mechanisms driving bedform formation and evolution across different environments. She's currently an NSF postdoctoral fellow here in the Jackson School, where she's working with David Morig and colleagues from A&M and Texas Tech on a project entitled Morphodynamics of Giant Dunes in Wind and Water. So we'll hear about some of this work today in her talk, The Morphology of Alluvial Sand Dunes. Take it away.
Wow, thank you, Marcy, for that wonderful introduction. So thank you all for having me today. I'm really happy to talk about my research in the morphology of alluvial sand dunes. But before I begin, I want to share a bit of a story, and Marcy kind of alluded to it. So when I was in high school, I really loved science. I took so many science classes, and I thought, this is something I want to do. I didn't know how to pursue that as a career. I wasn't really sure what that route looked like. And I found out about a camp at Texas A&M. It was a geoscience camp, and it was specifically for underrepresented students. So I didn't know what geoscience was, but I thought, cool. I didn't know what the word underrepresented meant either, but I thought, whatever, it sounds like a good opportunity. So I attended, and I experienced one of the most pivotal weekends of my life. I learned about geoscience techniques and tools, and I thought, wow, this is really cool. I had no idea this field existed. And in this image, I attended a Geology 101 lecture. And so you can tell I'm sitting in the very back. There's an arrow pointing towards me. And I was tired. It was an 8 a.m. 101 lecture. I was sitting in the back, kind of trying to stay awake. I hadn't had coffee. I didn't drink coffee at the time. And the professor put up this image of Aeolian dune stratigraphy. And he showed us these structures, these lines going downwards. And he said, this is Aeolian dune stratigraphy. This rock tells us not only that this was an ancient dune field, but the direction that the lines incline towards tell us the direction the ancient paleo winds were blowing. And in that moment, I was blown away. I made a decision right then and there that I was gonna be a geologist. And so I attended Texas A&M University for a Bachelor of Science in geology. I saw sand dunes for the first time at field camp, and I learned about sand dunes, conducted undergraduate research studying sand dunes in the equatorial region of Titan, which is a moon of Saturn, and I published that work in an undergraduate journal here. And so from that experience, I learned that I really loved research, and I wanted to do research more. So I thought graduate school is the way to do that. So I started looking for places to go to graduate school, and I found a school, University of Illinois, and the project there was about river dunes. And I thought, huh, I study desert dunes, well, it can't be that different. So I made a decision to go and attend graduate school there and make a switch from studying these desert dunes to now studying river dunes. And so what I'm going to share with you today is a lot of that work, the bulk of that work. I'll start off by talking about the basics of dune morphology and flow dynamics. Then I'll talk about the bulk of the work, which is the shape of dunes in the world's big rivers, possible mechanisms of their formation, and then the implication that those mechanisms have. And then I'll finish by discussing a little bit about some of the recent work that I've been doing at UT Austin. So to start off, we know that dunes exist in a range of environments. This is an example of aeolian sand dunes in deserts. This is an example of fluvial dunes in a river. These dunes, they form at the bottom of the riverbed, and we can actually see that in this case because this river is tidally influenced. So you can see these dunes moving through. And we know that in rivers, at least, these dunes make up one of the most common depositional products in fluvial systems, which is this cross stratification that we can see, these lines going downwards. That's similar to an image that the professor showed me in that Geology 101 class. And so when we think about dunes and their morphology, there's some basics that I think it's important to know. So if we have flow going from left to right, we'll have a gently sloping stoss side, and the top of the dune is the dune crest, and then we'll have a steeply sloping lee side. This lee side is often thought to be sloping at around 20 to 30 degrees. And then at the bottom of the dune, we have the dune trough. And so these dunes can range anywhere from 0.5 meter to 10 meters in height and 10 to even hundreds of meters in wavelength. Oftentimes in rivers, we'll have these smaller superimposed dunes that climb up the stoss of the large dune. And as that entire dune moves forward and sediment is deposited in the lee side, we get the development of 4 sets, which we'll see preserved in the rock record stratification. When we think about the flow dynamics of dunes in rivers specifically, there's a few key pieces to it. So when flow moves over the dune, it will detach at the crest and reattach somewhere further downstream in the trough or the following dune stoss. And in that area, we'll have a separation zone where flow is recirculating. A shear layer will develop between the separation zone and the following wake region. When flow reattaches, we'll have the development of an internal boundary layer along the stoss. And then maximum flow velocity is above the crest and expanding flow is above the trough. This is a great image, and I think it shows all of the basics really well, but I think it's easier to see some of these dynamics in video. And so here's a video from Mark Schmeckley's YouTube. We have dunes going into the page, and you can see the flow of moving over the stoss and recirculating in that lee side. And so from this video, you can see that the lee side is really important in determining the flow separation in that area and the turbulence that's advected off of that dune. And the lee side is interesting because more recently, there's been a lot of work to show that it's not a simple, straight line. There's a lot of complexity in these lee sides. And so Alice Lafair went to the Paraná. She's measured dunes by hand, and she's shown that this lee side is not simple. There's several different segments to the lee side, and generally there's some complexity to this. And so if we look at dunes from the Paraná River, this is a profile line. So this is distance on the X and then depth on the Y. Flow is going from right to left. Now, you can see in the Paraná River near Aguas Corrientes, we have these dunes that are kind of hump-shaped. Whereas near Paso de la Patria, we have a very defined stoss and lee side. They're different. It's the same river. When we look at dunes from the Vaal River in the Netherlands, flow is going the opposite now, and we can see we have a defined stoss and lee, and we even have some superimposed dunes that are growing on the stoss side. And so if we look at the lee side there, it looks like the lee sides we said, steeply sloping. But if we actually measure that lee side, we take into account the aspect ratio of this graph, you see that that lee side is only sloping at 11 degrees. That's very different than the assumptions that we make. We assume that these dunes are sloping at 20 to 30 degrees. And what we see here is this is 11. The fact that this dune is sloping has a lee side of 11 degrees, it means that this is a low angle dune. And so low angle dunes are really interesting because there's an evidence for a different fluid dynamics in these dunes. Specifically, there's an evidence for a lack of or an intermittent zone of flow separation. What do I mean by that? Well, in this image, I'm showing a rotating wing that's depicting the onset of flow separation. So as that wing increases in its angle, flow is going from left to right, you can see a point of separation develops, and as it increases in angle, the flow separation zone becomes bigger and bigger. And so when that wing has a low angle, we don't see flow separation, and then as it grows, we see it get larger. So several people have looked at, the different values of lee side angle and looking at flow over these lee sides and what happens and when do we see flow separation, when do we not? And the consensus is that permanent flow separation is absent for lee side angles that are less than 10 degrees. Now, when we think about dunes and big rivers, we often consider that dune size is related to the flow depth. And the relationship that we think is that flow depth is about 3 times the dune height. So when we think about big rivers, we expect to see large dunes. And that's what we see. When we look at dunes in the Paranal River, this is a bathymetric map showing dunes. Flow depths in this area go up to 12 meters, and we see dune heights that are up to 2.5 meters. And so we see big dunes, and that's kind of what we expect. But this is really important because dunes in these rivers, they comprise about 50% of the friction for these lowland rivers. And so it's really important that we know how big they are so that we can estimate what the friction is that they're exerting. But in the sedimentary record, we also have a relationship. We say that size of dune cross sets may be proportional to flow depth. The relationship that we think here is that dune height is 3 times the thickness of cross sets. What do I mean by cross sets? Again, this is a nice video showing cross strata development. So you can see these dunes are moving. And as they're moving, their lee sides are being preserved from these lines. And so understanding the size of dunes, understanding the relationship of dune size and flow depth is really important for predicting paleohydraulics of ancient environments from outcrops. And this is really important when we consider that this kind of information is essential for interpreting these ancient environments and hydrological processes. And a lot of this work has been done recently on these major outcrops to think about and really get an idea of even climatic variability in these ancient environments. Now, only recently has the bottom of the world's big rivers been revealed, and this is through the use of multi-beam echo sounder systems. So here is a example of multi-beam data being acquired from a ship. It's a nice diagram. The idea is that you have a multi-beam, the bottom of the ship, the multi-beam sends sound waves down as it's moving, the sound waves come up, the time it takes for the sound wave to go down, hit the bed and come up, tells us a distance. And when you do that and you move up and down these areas, you start to reveal a map. And so doing this has really changed our view. It's shown us that dunes are prevalent in these big rivers, that they're the major movers of sediment. And you can see that from this image here. This is again a image from the Paranal. In this video, or in this picture, the dunes are moving towards us. So you can see that there's ribbons of sand moving towards us. Now, when we have this beautiful data, we now need a way to measure the dunes. So several methods have been created to measure dunes, to measure bedforms in general. A lot of them, all of them work along single profile lines. And so these methods can range from, wavelet analysis, geostatistical methods like factorial kriging, a lot of signal processing methods, and then automated analysis using measurement rules with the bedform morphology in mind. So these methods are great, but there still exists a need for a computationally efficient and a spatially extensive method to quantify things like dune height, wavelength, lee side angle, and the flow depth these dunes exist in. But specifically, there exists the need for a method that preserves the morphological complexity that I've been showing you in these dunes. And so that's what I did in my PhD. I created the bedform analysis method for bathymetric information. We'll call it Bambi for short now. There's a GitHub link for it, and I can also share that with you if you're interested later. But what Bambi does is it measures the dunes across the entire river width of the river. And it outputs measurements of dune height, wavelength, lee side shape, lee side angle, the flow depth the dune exists in. And it outputs those measurements and georeferences them to the trough point. And so this is really cool because the fact that it's georeferenced means that we can do some really fun GIS stuff to it, spatial analysis. And I've shown you an example of that. I've plotted the output points again to the Paraná River. And you can see this is from a GIS software that I'm showing you. And so this has really changed the output, the amount of measurements and the amount of detail that we know of these dunes. You know, in the past, you would do some hand measurements of a couple of profiles. You'd run those methods on a couple of profiles. And you get a couple hundreds of measurements. But what Bambi has allowed us to do is increase that output to tens of thousands to even hundreds of thousands of measurements. And so I'll zoom in a bit here on an output, what this looks like. You might have thought that this was a line, but actually these are all individual points. And so they're measuring these dunes at profiles that are spaced across the entire river width. Now, the interesting thing that Bambi does that's different and unique to all these methods is that it really looks at the complexity of this lee side. And so it measures the mean angles and the max angles. So here's an example. If flow is going from left to right, we have a simple dune here. We have a simple lee side, a straight lee side, and it measures the mean angle, which is this blue tangent line, and the max angle, which is this red tangent line, and it's a simple lee side, so they're the same. But when we have a weird shaped dune, for example, a dune that has kind of two segments, a steep slope and an average slope, Bambi will measure the mean slope and then the maximum slope, and you can see that this maximum slope is different from the mean slope. And not only that, Bambi tells us where this maximum slope is. Is it at the top of the dune or is it at the bottom of the dune? So what I'm going to do now is I'm going to show you how we've used Bambi to understand the shape of dunes in the world's big rivers. These are some examples, some pictures of surveys that we did in the Amazon River, but this isn't the only survey that we've done. In fact, when I started my graduate degree, there were several groups across the world who had been running multi-beam surveys across some of the world's big rivers for about 15 years at that point. And jumping into this degree, it was a beautiful time where everybody wanted to work together, and they had all identified Bambi as the tool that could help us understand the shape of these dunes. And so some of the questions that we had were things like, you know, what do dunes look like in these rivers? What is their shape? What is their size? What can their shape tell us about the relationship between hydrodynamics and sediment transport? And finally, can their shape help us understand what these big dunes may look like preserved in the rock record? And so we were successful in doing this work where we showed that dunes in the world's big rivers are characterized by low angle lee side slopes in a complex shape. And we studied a few major rivers around the world, including the Amazon, the Paraná, the Missouri, the Vaal River in the Netherlands, the Mississippi, and the Mekong. And so what I'm going to share with you first are the measurements that we got from the lee side angle of dunes in these rivers. So these are histograms. The first column is mean lee side, and the second column is maximum lee side. And so here we have the Amazon River, Mekong, Mississippi, Missouri, Paraná, Vaal, and all of the rivers combined. And you can see on the x-axis, the lee side angles range from where we have an axis from 0 to 40. And so when we look at the mean angles, you'll see that a lot of all these histograms, they peak at this line here, which represents 10 degrees. And so the mean angle of all of these dunes is dominantly at around 10 degrees. And that's interesting because if you remember, 10 degrees is the value where if dunes have lee side angles at or below 10 degrees, they're not experiencing permanent flow separation. Now, if we look at the maximum angle values, you can see that those histograms have shifted. So the maximum angles are greater than the mean. They're about, on average, they shift about 5 degrees. But we don't see peaks in this sort of shadow area. And this is, you know, what we commonly thought lee side slope at 20 to 30 degrees. And you can see that even the maximum slopes are not really peaking here. And so this tells us that dunes are dominantly low angle in these big rivers. Now, if we look at another one, The location of the maximum lee side slope. So again, Bambi measures where this steep slope is, and it reports it as a fractional height of this height to the large dune height. So if a lot of the steep slopes are on the top of the dune and we plot that as a histogram from low to high on the dune, we would see a histogram like this, where we have values shifted towards high. Whereas if we have a lot of slopes that are at the bottom of the dune and we were to plot that in a histogram reporting the fractional height, we would see a lot of values shifted towards lower values. And so when we look at all of the values of fractional height of the maximum slope for all of the rivers, we get a histogram like this. And you can see this is peaked at about 0.4. And so this tells us that the maximum lee side slope is commonly located towards the lower middle half of the dune lee side. And this is really interesting because this tells us two things. It tells us that flow separation may be less significant if we have a steep slope, a brink point on the lower half of the lee side. And it's also really interesting because the maximum slope is going to be more likely to be preserved if it's on the lower half of the dune lee side. So that's interesting when we think about the rock record. Now, if we look at the relationship of dune height versus flow depth, remember this relationship is really important when we start to think about paleohydraulic reconstructions. And so this is flow depth on the X and dune height on the Y. Each point in this plot represents a dune measurement. And what I've plotted on top of this are lines where dune height is 1/10 of the flow depth, dune height is 1/3 of the flow depth, and dune height equals the flow depth. And so this dashed line is what we commonly think this relationship is. And what you can see is that it actually represents some of the maximum values for some of these rivers, especially these very big rivers. But if we look at the data in a different way, if we plot it in terms of a cumulative percent, and we plot H over Y here, the dune height over flow depth. If we look at all the rivers combined in this black line, and we look at the H over Y 90, that value is actually 0.127. So these dunes, it's interesting because, you know, we do see really big dunes in these rivers, but the majority of these dunes are just much more smaller. And that H over Y relationship is more likely closer to 0.127 and not 1/3. Now, bringing this all together, we want to know what the flow separation potential is of these dunes and these big rivers. And so the way we can do that is if we look at the relationship of lee side angle versus relative dune height, so dune height over flow depth. And this first area here where lee side angle is less than 10 degrees, we're going to have no permanent flow separation, and that's what we expect. That's what we see from the literature. And this area over here where lee side angle is greater than 24 degrees, that's where we're going to see fully developed permanent flow separation. And in between this area, it's a bit of a gray area, but we know that the onset of permanent flow separation occurs when values are greater than this line, which is reliant on both the lee side angle and the relative dune height. And that's also from the literature. And so this plot, what I'm showing is a heat map of the data from all of these rivers. And what you can see is we have a lot of the values are hitting right here at around this 10 degrees. And so what's that's telling us is flow separation potential is low for all of these dunes in these really big rivers. And so this finding really requires that we reassess how we incorporate flow separation in models that seek to predict flow resistance, water levels, and even flood risk. So to summarize a lot of this work, what we saw was that low angle dunes are dominant in big rivers and in deep flows. The maximum slope is more commonly located towards the bottom half of the dune lee side. Smaller dunes are much more common in these rivers, and this H over Y relationship is more likely 0.127. And all of this comes together and tells us that dunes in big rivers have a low potential for flow separation due to their low angles and their small relative dune heights. And so these morphological characteristics and their influence on fluid flow have profound implications for the models of flow, how flow resistance is predicted and modeled, and how the deposits of such dunes are recognized in the rock record. And so I want to share a few examples of how we can see the implications that this may have. Here I'm showing you some flow models that are reporting the turbulent kinetic energy, the TKE, of flow over lee sides with 10-degree lee side angles, 20-degree lee side angles, and 30-degree lee side angles. Blue is low TKE and red is high TKE. So you can see in the 10-degree case, we have very low TKE, whereas in the 30-degree case, we have very high. When we think about big rivers, this is what we expect because a lot of the dunes in these big rivers have lee side angles at 10 degrees, right? And that's interesting because the way that we model these rivers, we use this value of 30 degrees. And you can see that there's a disconnect between what we see and how we're modeling them. Now, when we look at the rock record and even just recent deposits, this is lines from parametric echo sounder lines. So these are shallow subsurface records in profile. These are from the Yellow River and the Bermejo River in Argentina. And so flow is going in this case of the Bermejo River, it's going from right to left. And we have lee side angles of 3.61 degrees, 4.48 degrees, and even low angle lamina here, 1.72 degrees. And so we see very low angles in these cases. And you can imagine when we're thinking about the rock record, how difficult it would be to tell the difference between something that's sloping 4 degrees and something that's flat bed, especially when we consider that a lot of the rock record that we see is this wide in cores. But the interpretations that we would make between those two, something that's low angle in a big river versus something that's flat bed, those are very different. We're talking about subcritical flow versus upper stage plain bed, supercritical flow conditions. Now, again, all of these are kind of assuming a very simple lee side. And so when we start to bring in the complexity of that lee side, this is work that Alice LaFair and I have started doing. We've looked at a case where we know flow separation isn't going to happen because these are very low angle dunes. The mean lee side angle is 5 degrees, but we wanted to see what happens when we add some shape complexity. So we added a steep slope of 10 degrees at the top of the dune, and then a steep slope at the bottom of the dune. What we're reporting here is turbulent kinetic energy. So blue is low, yellow is high. And what you can see is just by putting in a steep slope location and varying that location, you have very big differences in the turbulent wake patterns. So here we have a very extended wake, and here we have a very concentrated wake, but it's a very strong wake. And so adding this complexity shows us that the wake patterns are really changing depending on where the steep slope is. And we know from the big river data that we have varying locations of that steep slope, and we do have steep slopes there. So with that in mind, with that complexity in mind, how can we now use those dune shape parameters to understand the mechanisms that lead to shape complexity? So there are a few mechanisms that have been thought to create low angle dunes. I'll go through them very quickly at first, and then we're going to go through each one in detail to really assess. The first is the influence of bedform superimposition, where we could have complex flow interactions between large and small scale dunes. The second is the influence of sediment suspension, where we have so much sediment in suspension, it can either bypass the crest and deposit in the lee, or it can dampen the turbulence and deposit in the lee. And the final idea is that we could have lee side avalanches and grain flows that are controlled by flow depth, where in one case, they might promote low angle dune formation. So we're going to start with this lee side avalanches idea, and then we're going to go through the other two in order. So here, with these lee side avalanches, the idea, an avalanche is when you have a wedge of sediment that builds up at the top of the dune near the crest, and that wedge will break and we'll see an avalanche coming down. So in a shallow flow, the idea is that these avalanches are granular and they keep the formation of this higher angle on the lee side. But in deep flows, this avalanche can become liquefied, which allows it to travel further down, and it can actually promote a lower angle. And so this is a hypothesis, and it requires that we really assess this with real data. So if we look at the Amazon River, what I plotted here is dune height and flow depth versus lee side angle. These are outputs from Bambi. And then I've also included a plot from a colleague, Cristiano Galeazzi, where he's measured the lee side angles of dunes in the same area, and he's plotted them as box plots and given us different flow depth ranges. And so if we look at the dunes from in this case, and we look at flow depths, 50 to 60 meters, we see a lot of angles at 10 degrees, but we also see a lot of high angles, in this 20 to 30 range. So, they're not dominant, but they still exist. And the fact that these high angle dunes exist in these deep flows means that these liquefied avalanches cannot be the only control. If that was the case, we wouldn't see them. We wouldn't see high angle dunes in this river. Now, the second idea is the influence of sediment suspension. The idea is that we have so much sediment in suspension that either that sediment can bypass the crest and deposit in the trough increases and we have a lowering of the lee side angle, or we could have so much sediment in suspension, it actually dampens the turbulence, and that allows sediment deposition in the trough and lee side, which also lowers the lee side angle. And so several people have tried to understand the influence of sediment suspension, and they often do that by using this thing called a suspension number. And so a suspension number is the ratio of shear velocity over particle falling velocity. The idea is that if the suspension number is greater than 1, then we know that extensive suspension is occurring. And so I've included some plots here from Naxban and Hoytink and Bradley and Vendetti, where they have suspension number on the X and then values related to dune size on the Y. So dune height, and dune height and wavelength. And what you can see in this case, we'll look at this plot. With increasing suspension number, we have an increase in dune height. And then once suspension number is greater than 1, we have a decrease. You can see that again here for the height, we have an increase. This line is suspension number equals 1, we have a decrease. And so what this is telling us is that suspension is influencing something, at least it's influencing the shape, the size, the height, and the wavelength. And so that's good to know, that's interesting, we see an influence. But I wanted to take this a bit further and understand the potential transport controls on dune lee side angle. And so I used this really beautiful data set from Bradley and Vendetti, where they ran dunes across a range of transport conditions from flatbed all the way through to equilibrium and past equilibrium conditions for cases where sediment is being transported at the threshold of sediment motion, so barely when sediment begins to move, bed load dominated conditions, 2 cases with a mixed load between bed load and suspended load, and then finally a suspended dominated case. And so what we're talking about here is really the difference between sediment being transported like this, rolling along the bed, jumping, hopping, and sediment being transported like this in the water column, pulsing through. You can see a bunch of suspension here. And so the idea was, do these different types of transport actually influence the lee side angles? So what I'm going to show you now is the outputs of Bambi from running it across all of these maps, about 10 hours of maps, data taken every 10 minutes for all of these transport conditions. And in this first case, we have plots of flow depth over lee side versus lee side angle. The colors are the different transport conditions. The symbols are the different flow depth conditions that started at, and then these bolded values are the mean values of each experimental condition. So what this shows us here is we have a range of lee side angles from 10 to 30 degrees across a range of these laboratory flow depths. These flow depths are 15 centimeters and 25 centimeter flows. When we look at the relationship of the suspension number versus lee side angle, if we look here, you can see that the lee side angle is kind of high near this 20 to 25 degree angle value. And then when suspension number is greater than 1, we have a decrease in the lee side angle. So we see a suspension control or an influence on the lee side angle here. The cool thing about Bambi is because we measure all of the dunes across all of the conditions and all these time steps, we can make histograms again. So I'm going to show you more lee side histograms. You're probably tired of those. What I'm showing you here is all of the bed load dominated conditions and all of the suspended load dominated conditions across all of the flow depths. So the 15 centimeter flow depth experiments, 20 centimeter, and the 25. If we focus on the bed load dominated case for the 15 centimeters, you can see that we have pretty high values here, 20 to 30 degree lee side angles. And then if we go down to the suspended load case, you see that a lot of the values of suspended load, the lee sides are between 20 and 30 degrees. And so the lee side angle is lower in the suspension dominated conditions compared to the bed load dominated conditions. To take this point a bit further, we're seeing that low angle lee sides are forming in these very shallow flows. This is a 15 centimeter flow depth. That tells us that there's likely not a depth control because we're seeing very low angles forming in very shallow flows. Now, the last mechanism that I mentioned is the influence of bedform superimposition. The idea here is that bedform amalgamation can produce erosion of the dune crest and lee side due to bed shear stresses generated in the superimposed dune lee side. So when this small bedform is greater than 0.25 of the large bedform height, that small bedform can erode the crest and create a low angle reactivation surface by reducing that slope. What does that mean? So here you can see that this small bedform is pretty small. Its height relationship is pretty small compared to the large dune it's climbing over. And so the flow recirculation cell that is occurring in this lee side is not big enough to create shear stresses that can actually erode that crest. And so that small dune is going to move and deposit in the lee side. But in this case, you can see that this small bedform is actually kind of big. Its height is much more comparable to this large dune, and the recirculation cell in its lee side is larger. The shear stresses that are generated in that lee are great enough that it can actually erode this crest, and you can see it will reduce the lee side slope. And so in order to test this and to look at this, we have to look at a condition where we know no suspended sediment is occurring. So we can be sure that we're only looking at an influence of superimposition, right? So what I did is I looked at the threshold condition. So this is no suspended sediment transport is occurring in the laboratory flows for the 15 centimeter flow depth in equilibrium. This is an example of some of the maps that we're looking at during this time period, and this time period is time equals 160 minutes to 250 minutes after equilibrium. I pulled out a centerline profile of these dunes, so you can see these dunes. They're moving from left to right, and we're going to focus on this dune here that's highlighted in yellow. We're going to watch it through time. On this first plot to the left, what I am showing you is lee side angle versus time. The blue points are the large dune lee side angle, and then the gray points, when they exist, are the lee side angles of the superimposed dunes. So they only occur if the superimposed dunes are formed. The second plot is the ratio of the small dune height, the superimposed dune height versus the large dune height. And this line here is 0.25. That's that value that we said. If it's greater, then we can see some of that erosion happening. And so if we look at this dune here, from time equals 160 to 190, it's just migrating. You know, it's got a pretty high angle if we look at these values, around 24 degrees. Now, at this time of time equals 190, we see that superimposed dunes form. And the height ratio of the superimposed dune to the large dune, it doesn't reach 0.25, but it's pretty close. Now, during the time that those superimposed dunes move through and move over that larger dune, we go from 190 to 220, and you can see a huge decrease in the lee side angle of the large dune. We're going from 24-degree lee side angle to 10-degree. Then the superimposed dunes go away, and we have the formation of a higher lee side angle. And so this shows us that the dune lee side angle begins to lower when this relationship is close to 0.25, and it lowers by a pretty big amount. These lee side angles are lowering by about 14 degrees when these superimposed dunes are moving over them. So when we think about the possible controlling mechanisms that have been thought to create low angle dunes, we can say that the influence of liquefied avalanches is likely not a dominant control. And the reason is because we see these really high angle dunes in deep flows, and we see these really low angle dunes in very shallow flows. And so the fact that this mechanism relies on a depth control, it just doesn't make sense that that would be a dominant control, because we're seeing these different values across a range of flow depths. Instead, it's more likely that there's a relationship that, we see a dominance of suspended dominated conditions influencing low angle dune formation. And then when there's no suspension, we see that superimposition can actually lower these lee side angles. And so there's likely a balance that exists between the two, where when one is dominant, the other one is less likely important. And so all of this comes together, and we think about, the flow potential of bed load dominated conditions and suspended load dominated conditions. And if you remember, if a lot of values plot here, we have a fully developed flow separation. So a lot of flow separation potential. So we see a lot more flow separation potential in bed load cases than in the suspended load cases over here. And if we think about this, we know that, the experiments that we're looking at, they're really controlled. We know exactly what's going on because we're controlling every single thing. But we know that in rivers, that's not always the case. These rivers can change. They can change from having bed load dominated transport, suspended load dominated transport, and there's likely going to be a lot of these mechanisms playing together. And so a really good opportunity to really study these mechanisms at play is if we look at dunes and variable flows in natural rivers. And so I've had the opportunity to work in the Vaal River to sort of study this balance. And so this is a picture of me standing on the banks of the Vaal River in the Netherlands near Nijmegen. And you can see behind my head, that's a ship. And so the Vaal River is a very important shipping canal because it connects the North Sea to Germany. So ships travel daily up and down this river, transporting goods. And because of that reason, it's really important that the ships travel safely and efficiently. And so the Dutch government really wants to know how this bed is degrading, what the dunes look like, whether they're getting too big and whether it's not safe and maybe a ship would run into them. And then that would be really expensive because they have to go and dredge it. So for that reason, they've ran multi-beam data on this entire length, this 16-kilometer length, every 2 weeks for more than 15 years now. And so I've been really fortunate to have access to this data by working with researchers at Deltatis, specifically Tyann van Dijk. And from the work that I've done here, we've had a lot of really interesting, findings about shipping navigation, protocols that we could have, the responses that, we may be able to tell local stakeholders and all these things. But what I want to share with you today is just what's possible when you have such a beautiful temporal and spatially extensive data set, and really how that allows us to take what we see in the lab and really test it in these natural environments. I mean, you can imagine this is kind of like running a large-scale experiment. So I'll share very briefly what we're finding in the Vaal River. And what I wanted to focus on is when we know variable flows are happening, and that often happens during a big flood. And so I went to the data and I tried to find a time where a big flood came through in the Vaal River. And so I've sort of cropped out a bunch of data. There's a lot more time above that, but I want to focus on this time right here. So this is the hydrograph. This is discharge through time. Time's going downwards. You can see this peak here of the flood. This is a major flood in the Vaal, is about 6,000 cumex. So this is considered a big flood in the Vaal River. And I've highlighted this histogram here for the peak of the flood of lee side angle. And so the way we talk about floods, we talk about the rising stage of the flood and the falling stage of the flood. That's the, leading up to the peak and then after the peak. And when you look at the lee side angles, they don't look like they're changing by much. You can see these peaks are low. They're near 10 degrees. Kind of shifts a little bit higher during the peak of the flood, and then it goes back down to lower again. And that's kind of weird, right? Like you'd expect more stuff to happen here. The fact that they're all low angle means that we kind of have to think about, okay, what's going on? What are the mechanisms at play? And the interesting thing here is in the rising stage of the flood, we have increasing discharge. We know that that's when we're going to have the opportunity to transport more sediment. A lot of that sediment can be transported in suspension. But in the falling stage of the flood, a lot of research has gone into understanding what happens here. And what people have seen is that in the falling stage, this is when we see a lot of superimposed dunes forming, because these smaller dunes are able to re-equilibrate with this changing flow condition a bit faster than these big dunes can. And so they actually become overtaken by smaller dunes. And so what we're likely seeing here, the fact that these lee side angles aren't changing, this may be an example of the balance between the influence of bedform superimposition and suspended sediment at play, both of which are keeping these lee side angles really low across the flood. So to summarize this work, we saw that Bambi offers robust measurements of dunes from high spatial and temporal bathymetric data. Using Bambi, we showed that dunes and alluvial channels have low angle lee sides and small heights compared to their flow depth. When we think about the mechanisms that lead to low angle dune formation, we can say that the influence of lee side avalanches is likely not a dominant control, and instead there's a balance between the influence of sediment suspension and bedform superimposition. When we think about what this means and we bring it together with the potential for flow separation, we see that flow separation potential is lower than previous estimates in rivers and in suspension dominated flows. And of course, when we think about all the complexities of rivers, how complex they are, how much they change, we know that things are going to change when we start to incorporate differences in grain size, the influence of flow hysteresis from floods, and all of the other really fun and complicated spatial temporal variations that we know are common in rivers. And so this sort of wraps up the bulk of this talk, but I want to kind of take us full circle and go back to the beginning of this story. I'm a very goal-oriented person. So about 7 years ago, I wrote in a personal statement, I said, I aim to balance myself as a researcher who in the future stands on the edge of both aeolian and fluvial geomorphology and is one day capable of bridging the gap in the research. And I'm very proud to say that that's what I'm currently doing at UT Austin. I've received an NSF postdoctoral fellowship to study the morphodynamics of giant dunes in wind and water. And I'm working with colleagues at Texas A&M, Texas Tech, and then here, of course, at UT Austin. And so the general idea of this project is we know that simple and compound aeolian dunes exist in deserts. We see them, simple cases in white sands, and then we see compound dunes in deserts like China. So these compound dunes are cases where you have smaller dunes moving over really big giant dunes. And we also know that simple and compound dunes exist in rivers. We've seen a lot of that today. In this case of the Mississippi River, this is the same part of the river during two different times. And you can see we have a simple dune and then we have a compound dune. And so the interesting thing about these giant dunes in deserts is that they move really slow. So here's an example of these giant dunes in Algodones Dune Field, California. It's in Southern California. There's a kilometer scale bar there. These dunes are really big, and you can see they have smaller dunes moving over them, but they move really slow. It's really hard to figure out how they're migrating, because when we look at them over temporal scales, we can't really see how quickly they're moving, but we can see how these smaller dunes are moving. It's really important to know how this entire system is operating, because the sediment flux and the ways that sediment is moving through this system helps us understand how we need to manage it. So if you see here, this is actually a railroad coming around it. There's roads that border these big giant fields, and these deserts actually even encroach on, cities. And so it's really important for us to know how sediment is moving through these systems and what kinds of management strategies we need to have. The fact that we don't know how these big dunes are moving gives us a problem. But the idea here is if we can use what we know about how small dunes influence larger dune shape, how they influence the migration and movement of big dunes from rivers, then maybe we can use a little bit of that knowledge to start to assess how we can use the movement of these small dunes in these deserts to understand the movement of the larger, greater dunes. And so I'm proud to say that I've run Bambi on these dunes, and what we're seeing is outputs of Bambi measuring the small dunes that are moving over these large dunes. And it works pretty well. It tells us some really interesting things. We can see some variability in the dune height. What this is telling us is that, there's a spatial variability in sediment flux across this area. And this is really exciting to be able to have. We've never been able to see this at this kind of detail. And really, what this is giving us is a really good jumpstart for the field surveys that we have planned in November, where we're going to be doing some on-the-ground measurements of sediment flux, wind velocity profiles, and we're hopefully going to be running another LiDAR survey out there. So I'll keep you updated. Hopefully I can come back and give you a bit of an update on that. But with that, I'd like to say thank you all, and I'd like to acknowledge my funding sources, and I'm happy to answer any questions. Yes.
Yeah, great talk. I'm curious about the flush thing.
Yeah.
Go ahead.
Is that on? Good. Great talk. I'm curious about in the flood stages, like in the Vol River.
Uh-huh.
It looks like I guess, heterogeneity of the heights, your curve kind of flattens out a little bit. So that maybe that's a component of erosion, maybe that's a component of secondary bed forms. What is causing that change in the heterogeneity of the
And the histograms?
Yeah, in the histograms?
Yeah, so a lot of so when you think about that, it's a change in the skewness and the kurtosis of these histograms. So I've done a lot of plotting of these and trying to understand what may be happening and thinking from a process-based view. What I think is happening is that during this falling stage, you can imagine these dunes are moving because there's a lot of flow moving in the peak flow. And then everything kind of shuts down. And then the dunes, they kind of stop and sediment starts to fall down. And so you're getting a lot of almost draping instead of active migration. When you think about the relationship of migration versus aggradation, you're getting a lot more aggradation in the system. And so I think what we're seeing is that on top of the fact that you have these smaller dunes that are starting to form, and they're kind of growing but not changing very quickly because they're being outbid by this falling out. And we're seeing a really big range in some really high angle dunes because these small dunes just formed and they're kind of getting a jump start on their formation. But then you're seeing a lot of really, really low angle dunes from the draping that we're seeing on this sort of deposition falling out. So I think that's what we're seeing. One of the things that we see in that case is just like a lot of these really high angle dunes. And those high angles come from like really small dunes that are just forming and they're very high angle. But eventually they get bigger and they sort of flatten.
So I guess a follow-up, if a manager of that system wanted to ask,
Mhm.
do we have more or less sediment in a particular area of the river after a flood?
In a particular area of the river? Oh, that's a great question, because we know that during floods also these rivers they kind of overtake their banks and sediment begins to kind of wash out onto the banks as well. So because of that, I would say we have less. But it's a bit of the Val River is a bit of a complicated case because we do have shipping. And so because the ships are sort of traveling up and down this river, on one side of the river, they travel very low because they're very heavy. And so they're traveling on the right side. And then when they drop everything off on the other side, they're very high traveling because they're light. So what we see on the side where they're traveling very low is there's a lot of resuspension of sediment. And because of that, in that area, we see a difference in the grain size because all of the very fine sediment, when these ships are moving over during these high flows, they're throwing that sediment up and throwing it onto the floodplain. And so not only is there a change in sediment supply, there's a really big change in sediment grain size across the width of the river because of all of these dynamics at play. So, yeah.
Great, thanks for the great talk. I was wondering, you showed that you had some turbulent kinetic energy in both for low and high lee angle slopes.
Mm-hmm.
But I was wondering if there is some kind of transition where you almost go to laminar flow when you have lower lee angles.
Yeah, that's a great question. And these lower lee side angles, laminar flow where you wouldn't have any turbulence happening. So far, we don't see that. So far, we see generally because there's a change in general bed level even because it's low, you have a flow constriction and expansion, which still creates a bit of a wake, a bit of a resistance. So when you think about the difference between that flow and a laminar flow is you'll see a momentum loss across the topography of that flow. So generally, we still see that momentum loss, which means that it's still technically not laminar, but we're not seeing like a super well-defined shear layer that we see from these really big flows, flow recirculations over these big dunes. So.
All of these multi-beam maps show me how three-dimensional they are.
Yeah.
So I've got a question about, you look at these wall you don't see any 2-week rendition that even look remotely the same.
Yeah.
So how about sidewalls?
Ah.
A lot of this work has been done in flumes and things. You see 2-dimensional renditions of flumes, but we always used to worry about sidewall stuff. So how about the sidewalls of these rivers to make them 3-dimensional?
Yeah, so you mean like the sidewall influences on the flow?
Or sidewalls of individual dunes with each other?
Yeah, so you're right. In the images that I showed you of the dunes moving through and those maps that I'm showing you kind of repeat, you're not going to see the same dune, and that's because what I'm showing you is like 300 meters in that area. But if you look at the 16 kilometers cases, you can see them moving through. But there is something to say about the three-dimensionality of these dunes. So in some of these rivers, the Amazon, it's a really wide area, and you're going to have a lot of three-dimensionality, a lot of secondary flow currents that are happening. In the Vaal River, it's a different kind of story, and that's because the Vaal is very controlled. So what I'm showing you from the multi-beam, and the multi-beam that's gathered in the Vaal is the very center of the channel. It's essentially the navigational channel. There's actually a lot more on the outsides of the river. And those outsides, the sides of the river, the banks of the river there's, I think, spaced every 100 to 200 meters, a dike that's angled into the flow. And so there are some cases where they've run multi-beams across more of the river width and not just the navigational canal, you start to see some influences from the sidewall, specifically flow coming off of those groins. And they call them flame structures, where you're getting a lot of erosion that looks like a flame structure just because of the angle of the groin and the secondary flow recirculation and enhanced shear on those cases. So far, I've spent a good amount of time trying to see if there's an influence from those groins leading into the center channel of the dunes. So far, you don't see that. You see that the dunes are moving through and not being really affected by this really high area that's been eroded. There's a case to be made that maybe some of that work needs to be looked at a little bit more clearly. But so far, for example, what I would be looking for is if there's a high area that's connected to these groins or something, an area of consistent aggradation or consistent erosion. And we don't see that. We see that in the center of this channel, at least, these dunes are moving through. And specifically in the Vaal, those dunes are actually much more two-dimensional than the cases in other rivers like the Amazon that we see. And I think that has to do with the width of the river. It's a lot more narrow than other rivers.
Thank you.
Any other questions?
Any questions from our online participants? Oh, Dan, would you mind unmuting yourself? I can't see.
Hi, can you hear me now? Doesn't sound like you can hear me.
Yeah, no, we can't hear you. I'll read your question. Dan Haynes asks, do you think Bambi might work on multi-beam surveys of dune fields in the coastal ocean? Yes,
it does. We've been doing a lot of work, working with colleagues who study tidally influenced areas, seabed cases. I'm working with a group a lot of people are really interested in these bedform analysis methods, and there's a group of us early career researchers who have kind of created our own methods, and now we're working together to bring them all together and build sort of a bedform analysis toolbox. And so in order to do that, we've been testing our methods on each other's data sets. And we all come from different environments, I would say. I'm a river person, so I would think about it as a unidirectional flow. And some of these people are, tidally, so kind of combined flow, and others are bidirectional flows. And we've worked on it together. We've been doing a lot of comparing the sensitivities of our methods. And so far, Bambi works on a lot of these methods. The one thing that you have to keep into account with these bidirectional flows is that Bambi will work in one direction and give you the least side values. And then if you want the opposite, you got to run it the opposite way. So it's a little bit of a headache working on changing that and adding a bidirectional component to it. But so far it works.
He says thanks.
Okay.
Any other questions from our online participants?
Thanks, Julia.
Thank you. Perfect timing because my computer is like about to die.